Welcome to Quantum Tech Investment and Applications, the podcast. I'm your host, Bob Sutor. This is produced by Katie Sutor and brought to you by our company, Sutor Group Intelligence and Advisory. This is episode 2025, 11/20. That is, I've recorded this on Thursday, November 20th, 2025. And the title today is Noise Happens, the fuss about error correction and quantum advantage. Well, why am I bringing this up today of all times? There have been some announcements this week, really about the state of quantum error correction, but also looking forward to what fault tolerance means in terms of connected quantum computers. But let me go way back before we even talk about this. Let's go back to 1867. So that's quite a way back. And for those of you who are watching as opposed to just listening, I'm showing a picture of the time of the first U.S. transcontinental telegraph line. And, well, this replaced the Pony Express. That is, men on horses or women sometimes bringing messages from town to town. And that was communication. And the telegraph came in. And they were wires, they were on poles, they went across fields, they went up and down mountains and things like this. And these were pretty buggy. That is, errors would happen. You could expect a certain amount of static in them, and it really wasn't very clean. And in fact, even when we graduated from the telegraph to the telephone, noise on the lines often made conversations very difficult. And the original telephones were extremely large, probably about, let's say, 1.5 feet wide by about 2 feet or so high. They had these massive batteries in them. And these were quite common into the 1920s, 1930s, and so. And eventually, telephones got better. But by the 1950s, people started thinking about using these telephone lines to communicate data. And it's one thing to be listening to a conversation, and you can kind of tell what people are saying. But when you're exchanging data, all those zeros and ones, if errors start getting introduced, the data changes, right? So if you just think of, the normal letters in the alphabet and punctuation and things like that, each one of those is a byte, 8 bits, that is a 0 or 1. And if you start changing those zeros and ones, the letters that you think you're sending are something completely different. So people had to start thinking of ways of getting past the errors that are inherent in the communication lines, the physical hardware that was involved with this. Now, the reason I bring it up this week is that Riverlane launched their quantum error correction report of 2025. I was one of the people that they interviewed for it. This is a great report. Just like last year's report, Riverlane can always be counted on to have some really, really good information about quantum error correction because that's their business. And rather than go into the entire story of what quantum error correction is and so forth, download this report. If you simply look for Riverlane Quantum Error Correction Report 2025, you can get it. If you are viewing this, I offer a QR code and so forth. Now, this notion of error correction, as I mentioned, we needed it classically. We still use it classically. We use it when we store information, store the videos on your phone and things like this. We use it in communication networks. There are lots of ways where these zeros and ones can flip. Bit flips, we call them. That's baked in and it's very well understood. There's this whole notion of error correcting codes where we can detect so many errors, we can correct so many errors, and as long as we can correct more of them that are happening, we're in pretty good shape. Now, as you need to correct more and more, you need to send more and more information. That is, somehow you need redundancy in the system to do this. When you do this with quantum computers, a lot of the classical methods don't work. And it all comes down to this no cloning theorem, which is one of the strangest things that people discover when they first start doing quantum computing. And the idea is that if you take an arbitrary quantum state, So that is the information that is stored in a qubit or perhaps multiple qubits. You can't copy it. You get a contradiction in the mathematics if you try to do this. And this goes back to quantum mechanics. This isn't that we're incompetent in some way. You just can't do it. So if I have information that's represented in a quantum computer, I can't just hand it off to you somehow, keeping a copy for myself. I can, through various methods, such as teleportation, actually send it over to you, but that destroys my copy as well. And this inability to do this copying means we have to get much more clever about how we do error correction. And so there are a couple of different ways of doing it. One way is we make up for this redundancy somehow within the qubit itself. These are sometimes called, in some situations, bosonic codes. If you look at what Nord Quantique does in their qubits, this is an example of that. And the other way, which is almost entirely what people talk about, is you get lots and lots of the physical qubits, the actual qubits that are implemented somehow in the quantum computers. And then you do put an error correcting code on top of these, however many qubits you need. And you can significantly increase the fidelity. Now, fidelity is a very optimistic, positive way. It's 1 minus the error rate. So if you have a 99.9% fidelity, that is one error in 1,000. All right. So if you go 1 minus that, that's how that works out. And people say, oh, look at my great fidelity. Well, okay, we're just not thinking about the error rate. 1 in 1,000 means if I do something 1,000 times, on average, one time there's going to be an error. Now, that may not sound so bad, but when I'm doing quantum computing, I'm not doing things 1,000 times. When we eventually think about quantum advantage, we're going to be doing millions of operations, and we're going to be doing it on hundreds of thousands of qubits. So our error rates have to improve. The fidelity has to get higher. And by doing quantum error correction, what we can do is we can do multiple qubits in the outer case, if you will, to get to what we call logical qubits. Now, the definition of a logical qubit is a little fuzzy. Sometimes vendors define it themselves. Basically, it just means almost like a virtual qubit that we've composed of other qubits plus software with a better error rate. It does not mean that they're perfect, but it could mean that instead of having 1 in 1,000 or 1 in 10,000 error rates in physical qubits, we get in our logical qubit an error 1 every billion times. And that, of course, is much better. The qubits that you read about in books such as mine, they tend to be perfect qubits, right? You read the book, you put the information into them, and they just stay forever and ever and ever. So this report is very important. It's the state of quantum error correction. I encourage you to read it. You'll learn a lot more about what they're really talking about with quantum error correction and how to do it and so forth and things like this. Now, the end goal isn't error correction. The end goal is fault tolerance through error correction and through other methods such as error suppression. Don't let the errors happen in the first place. Error mitigation. Make up for them as you kind of go along and then ultimately detect and fix errors, right? So all this fit together into what we call fault tolerance, which means if something bad happens, somehow we can recover from it. And this means that whatever it is we're trying to compute, we can do so with sufficient accuracy to get the answer that we want, right? So do remember this, that QEC, quantum error corrections, is just a tool to give us fault tolerance. And it's this fault tolerance that will allow us ultimately to have long-running quantum computations on potentially a lot of data. We can't do that right now, but that's what it will give us. So the second announcement this week is that IBM and Cisco announced plans to build a network of large-scale fault-tolerant quantum computers. And that's the headline from the IBM newsroom. So here the idea is that, well, all right, let's say we have a fault-tolerant quantum computer. How do we make it talk to another fault-tolerant quantum computer? Right? They're different devices. You can't just run a wire between them, right? You can't just run a simple optical cable between them. Classical networking doesn't work because what we have to send between them is quantum information, right? And that's very different. So we have to take the information that's in the quantum computer. In IBM's case, it's a super conducting quantum computer using Josephson junctions. We have to take that quantum information, move it onto a photon. Then we can use optical methods to move that information someplace else. Now, you're not necessarily sending the photon all the way across to something else. You may use entanglement in the middle to transfer the information and so forth. But the idea is that you need to do quantum networking. Now, when you do this transduction, you go from quantum information held with one modality, in this case, superconducting, to photonic. Errors can happen as well. Because you're doing some sort of operation, you could move the information, but it's not quite accurate. So let's just imagine a classical example is that we start with the number 1.0, and when we move it over, we get 0.99. That's not so great. We'd like it to be as exact as possible. So once again, this notion of error correction, fault tolerance comes in not only with the computers themselves and inside the computers, but how we communicate between them. And that is a thorny problem. People are only now starting to look at this. I will say, and this is a disclaimer, I am on the board of directors of a company called New Quantum in the UK, and they are looking at doing this transduction from ion trap quantum computers, right, into for photons and then doing the communication. And other companies are doing it as well. The future, therefore, of quantum computers, quantum computing systems, isn't simply just making one big system. It's networking them together. Now, it may mean for some vendors that they will build big quantum computers by networking together smaller ones. Or even if you have a big one, you're going to network it with other big ones and make a quantum supercomputer, if you will. So just as it is in the classical world, we can talk all we want about processors and computers, but networking is part and parcel of what we do and what we mean when we talk about computers. Now, with all of this, always a question of what we mean with quantum advantage. I have very mixed feelings about this. I tend to use the term practical quantum advantage, meaning I really don't care about esoteric examples in the back of the lab that perhaps 47 physicists in the world understand. I want it to be something that applies to people in their everyday lives. When will that happen? Well, right now, there's just this rapid communication of a little bit of quantum advantage here, a little bit there, whatever. And I'm going to term this micro quantum advantage if it's really true. Right? I don't know if it's really true. Lots of people are claiming this. Maybe they're claiming it because they're amazed it's wonderful. Maybe they're claiming it because they want to be in the history books. Maybe they're claiming it because they want their next investment round. But it's not the end game. At some point, we are going to move from this period right now, this NISQ period, this where we have noisy qubits, to a period where we have fault tolerance enabled by quantum error correction, other techniques. We're going to do it at scale. We're going to have enough qubits to do interesting things. And that is when what I would term the golden era of quantum computing will begin. And then, as IBM and Cisco announced, we will start networking these together. And so it's probably, I would guess, the mid-1930s. Excuse me, the mid-2030s. And I'll tell you why I said 1930s. It's this example. I went and I looked up the history of televisions because I thought, there must be some comparison here with technology as it evolves. So I went and I looked it up. And in fact, I used Anthropic Claude and I did some other references and things like this. It turns out that a lot of the basic technology for televisions goes back to the 1920s and 1930s. And in the late 1930s, people started selling these. The commercial era of television began. Can you imagine what a television was like in 1939? And the source described these as very expensive and very small, and there wasn't a lot of programming. Well, in that case, they meant there weren't a lot of shows to watch, right? Not code. And then World War II happened, things slowed down, but it was really the 1950s where this started to take off. But these were, for the most part, black and white televisions with these large, heavy tubes, cathode ray tubes. And then in the 1960s and the 1970s, color televisions came in, but they were still these heavy things. And now compare to perhaps your television, your computer screen, the screen on your mobile phone, there is a huge, huge difference between what we think about displays and what it was like nearly 100 years ago. I'm sure there were many, many wonderful ads about this commercial age of televisions in the 1930s and early 1940s. Maybe we're not quite back that far, relatively speaking, but these are early days and people are making great claims and there's a lot of tremendous work that's being done. I get that, okay? But in the 2030s, the mid 2030s, is when I think this will really start coming together for quantum computing based on quantum error correction, based on other technologies, quantum networking, general innovations, material science, and then we'll see what we have. So be optimistic, be positive, look through the hype, smile when you hear something that's maybe just a little too ridiculous to be true, but okay. I think it's all going to work. I think it's all going to come together. Now, I do explain a bit about quantum error correction in my book, Dancing with Qubits, the second edition, particularly the easier ways of doing it that goes back about 30 years, what the problems are, how you do these things, and a little bit of a nod to current error correction techniques. A lot of the quantum error correcting codes today require a fair amount of mathematical background to describe exactly how they work. But let me just say it's this replacement for the redundancy, if you will, of classical codes that you have to make up for somehow, some way when you are doing this. Now, this podcast is part of what we offer on Substack. This is the podcast version of it. If you just look for Sutor and Substack, you will find it very, very quickly. Yes, we link to these episodes here, but we also have reports. We have earnings reports, commentary, and what I hope a lot of you have subscribed to are the daily quantum updates. These are completely free. We automate picking up a lot of the news about quantum computing as much as we can fit. Frankly, there's so much lately. And you can subscribe, and every weekday you can get an email and it tells you the latest and most important news. We curate this a bit to not overload what you are trying to do. This podcast is open for sponsorship for companies, organizations, and conferences. Contact Katie Sutor at katiesutor, KATIESUTOR @sutor.com for details. Now, there are various legal things that apply to this and everything else we do. I generically just call it legal stuff. And if you visit sutor.com, that's a short name for our company website, you can find all the legal information and disclaimers, disclosures, and so forth. So thank you very much for joining us today. I hope you learned a little bit more about how quantum error correction fits into fault tolerance and eventually networking as well. Take care. Until next time.